Hello everyone, welcome to week 8 live session of NPTEL's Digital Circuit course. I am Om Maheshwari and today we will be discussing some questions which may help you in your assignments as well as your exams. So mainly in this week we will focus on finite state machines as well as data converters, mainly DACs. So let us start the questions. So the first question is, which of the following options represents the fastest ADC? A. Counter type. B. Flash type. C. Successive operation approximation. D. Dual slope type. So, if you have gone through the video lectures, you might know that Flash ADC is the fastest. It has comparators for each bit. So, for each bit of analog to digital conversion, it has a separate uh, comparator. It has separate comparators. And for n bit, wait, multiple comparators. And for n bit conversion, it has 2 to the power n minus 1 comparators. For example, for 3-bit analog to digital conversion, it has 8 minus 1, that is 7 comparators. And since all these comparators work in parallel, it is the fastest. So next question is, which of the following ADC is more expensive to build? And for the same reason, because it requires maximum amount of comparators, it is the most expensive. Okay, so next question. For a 3-bit weighted register, so this is a weighted binary register. DAC. The circuit is shown below. What can be the values of R0, R1, R2, and RL respectively? So in a binary weighted register DAC, we have something like this. We have some load resistance RL. This is, let's say, Rn, Rn minus 1, R, R1, R0. So typically, this is MSB and this is LSB. Now, uh, in binary weighted registers, if let's say R0 equals to R, then R1 will be R0 or R by 2, and similarly R2 will be R by 4. Similarly, Rn will be R by 2 to the power n. and typically RL is much greater than R0. So with these concepts in mind, where uh, registers are like in this increasing order and RL is much greater than all of these. So we can answer this question. So what can be the values of R0, R1, R2 and RL? So values should be such that if R0 is some value, R1 should be half of it, R2 should be half of this, and similarly the last one would be much smaller and RL will be much more than all of it. So in this example, if we see it's 100, then 50, then 25. So this is in the order that we are looking for. These are in divided by two orders, which is what we want here. And RL 1 megohm is much greater than all of these. So option B is the correct answer. R0 equals to 100 kilo, R1 is equals to R0 by 2, which is 50 kilo ohm, R2 equals to R0 by 4, which is 25 kilo ohm, and RL is 1 mega ohm. Okay, so again, this was much of a theoretical question. So let us move ahead with the next one. In the below R2R ladder DAC. So why it is called R2R ladder DAC? Because we have resistances in this format R2R, or in all the series resistance are R, or the parallel resistance are 2R. So this is why it is called R2R ladder DAC. RF equals to R and VREF equals to 10. If the analog output voltage VA is 9.37 volts, what is the binary input at V3 MSB to V0 LSB of the DAC? Okay, so let us call these fixes at V0 dash, V1 dash, V2 dash, and V3 dash. Okay, so this has two parts. First is this R2R ladder. So resolution of the R2R ladder ADC is Vref by 2 to the power n. N is the number of stages or number of bits. So here we have 4 bits, 0 to 3. So it is 10 by 2 to the power 4. Vref is given in question as 10 volts. So this is 10 upon 16. Now the VA is the output, right? So output is resolution into VA. So VA is given as VA equals to resolution is given as 10 by 16 into V in. So VA is 9.37 equals to 10 by 16 into V in. And if we solve this, we get V in equals to 15 volts. Now, what this means is, in essence, you have applied some binary equivalent worth 15 volts here. Now to find this v0 dash, v1 dash, v2 dash, v3 dash, we must convert this 15 into binary form. And 15 in binary form is 1 1 1 1, right? So v0 dash, v1 dash, v2 dash, v3 dash is 1 1 1 1. Right? So here we have 1 1 1 and 1. Now our actual inputs v0, v1, v2, v3 are binary to gray to binary conversions of these numbers. So your v0, v1, v2, v3 will be gray to binary conversion. So for 1 1 1 1, if you want to convert it to binary form, if this is in gray, what you can do is you write this is MSB, this is LSB, you write MSB as it is, then do XOR of these two. XOR of these two is 0. Again, XOR of these two is 1. Then XOR of these two is 0. So your answer is 1 0 1 0. So this is your V0, V1, V2 and V3. The final answer here is 1 0 1 0, which is option A. Okay. Okay, it is from MSB to LSB, so it is 0 1 0 1, sorry. Uh, just a moment, let me check. Okay, this is MSB, this is LSB. So this is V3, V2, V1, V0, and your answer is A. And 0 1 0. Okay, so everything remains same, just I've changed the position, interchanged the positions of V3 to V0 because V3 is MSB. I was considering V0 as MSB earlier. So your answer is 1 0 1 0. Is this question clear to all? Payal has given the right answer. All right, then let us see the next one. So one thing to note here is one very important thing to note. The resolution of R2R is Vref by 2 to the power n. So this is true only for R2R. So for R2R DAC, resolution is Vref by 2 to the power n. For all other DACs, resolution is always Vref by 2 to the power n minus 1. This is a small thing, but it would be good if you remember this. This minus 1 is not and with n it is -1. Okay, so next question. You have a 16-bit DAC and it is calibrated over full range from 0 to 8 volts. If the input to the DAC is DEC, is something in hexadecimal form, the output is what? So if anyone wants to try this, you may try for a minute, then you will solve this. Okay, so let us solve this. We have, so first let us look at what is this decimal number. What is this hexadecimal number in decimal form? We have DEC base 16. If you remember in hexadecimal, after 0 to 9, we have A, which corresponds to 10, B, C, D, E, and F is 14, sorry, 15. So we have DEC. We want to convert it to decimal. So D is 13. 13 into 16 to the power 2 plus E is 14 into 16 to the power 1 plus C is 12 into 16 to the power 0. So this is your input V in. V in will be, if we solve this, it comes out to be 3564 base 10 volts. So your full scale range is VFS equals to 8 minus 0, which is 8 volts, and which is simply your reference voltage, you can say. So your resolution will, your V out will be VFS upon 2 to the power n minus 1. This is simply your resolution into V in. So basically what we are doing here, you had this 0 to 8 volts, you divided it into 2 to the power n minus 1 parts, and which corresponded to the resolution, and now we are counting this 3564, where does it lie when mapped in this range. Okay, so V out is given like this, so it will 18 upon 2 to the power 16 minus 1 into 3, 5, 6, 4, and this gives you on solving 0.435 volts, which is option C. So Payal and Harsha have given the right answer. Does anybody else have any doubt in this question? Okay, so let us move ahead. The question says, for a flash ADC circuit, which among the following figures denotes the relationship between the number of bits in digital output and number of comparators required? So in the y-axis you have number of comparators, and in the x-axis you have number of bits in ADC. So you have to tell which of these figures corresponds to flash ADC. Payal has a question. If the type of DAC is not mentioned, do we assume it anything other than R2R? Since the formula is different for both. Yeah, you can assume it anything other than R2R. And anyways, for this question, it would not matter much if you take it to the power n, you to take it to the power 16 or to the power 16 minus 1. You will get almost same answers. In most of the questions, it will be true. Whether you take 2 to the power n or 2 to the power n minus 1, you will get almost same answers. But yeah, prefer to take this when it is not mentioned. Okay. So coming to this question, Harsha says figure 2 is correct. Do we have any other answers? Okay, so let us get into it. So figure 2 is actually wrong. This is not correct. So if you remember, flash ADC, flash, yeah, flash ADC circuit, what you have, if number of bits is n, number of comparators required as 2 to the power n minus 1. You need 2 to the power n minus 1 comparators in a flash ADC circuit. So if let's say your number of bits are 3, you will need 8 minus 1, which is 7 comparators. The number of bits are 4, you will need 16 minus 1, which is 15 comparators. So As you can see in figure 3, it is like constant number of comparators with number of bits. This is incorrect. This one is linearly rising. This is also incorrect, right? And if you see this one, this is like something like exponential 2 to the power n minus, probably 2 to the power n minus 1. So this is correct. The number of components increase exponentially for flash type ADC. So if you want to see flash type ADC circuit, I think I have one question. Yeah. So this is a flash type ADC. So sorry, this is DAC, but same thing. So you have like here for a 3-bit D0, D1, D2, this is 3 bits. You have 7 comparators. We'll get into this question later, but I was just trying to show you. So in flash ADC, the number of comparators rise exponentially, right? This is in exponent. So your answer is figure A. It does not increase linearly. It does not constant. It is exponential. Is this clear to all? You can also check these values also. If you want to verify, like for 8 bits, you would need around 255 comparators. For 7 bits, you would need around 127 comparators. For 6 bits, you would need around 63 comparators, something like this. Whereas in this case, for uh, I think for 4, it is 7 comparators. For 5, I think it has uh, 9 comparators or something like this. So you have to be careful with reading the graphs. Okay, so next question. An 8-bit successive approximation register type ADC is used to convert 4.75 volts to digital output. The reference voltage is 12 volts. The output of the ADC at the end of third clock pulse after the start of the conversion is. So what you have is a successive approximation type register type ADC. And what you do is successive approximation means you approximate answer in each clock cycle. So you first approximate what is could be the output, then you check, then you approximate, then check. So like this it works. So if you have saw the videos, you may be able to solve it. So if anyone wants, they can try for a minute, then we will solve it together. All right, so let us solve this question. So we know we have 8 bits, so n equals to 8, and Vref is given as 12 volts, and Vin is 4.75 volts. We have to convert it into digital output, and the resolution what we will have is equals to Vref by 2 to the power n minus 1, which is 12 upon 2 to the power 8 minus 1, and this is 0.047 volts. Okay, so when you start using this SR ADC, you start at, let's say, clock equals to 0. You start with 8 bits. So these are your 8 bits: 1, 2, 3, 4, 5, 6, 7, 8. This is MSB, LSB. So how you started with is right. Uh, in the next clock cycle, what you will do, you will change this 0 to 1, and this corresponds to 2 to the power 7, and you multiply. So this the value voltage value corresponding to this will be 2 to the power 7 into resolution 0.047. To solve this, it comes out to be 6.023. Now the 6.023 is greater than 4.75. So since it is greater than 4.75, what you will do is you will uh, you will flip this bit. You will not retain this. You will make it 0 again, and you will change this one to 1 then. So in the next clock cycle, what you will do, this one remains 0. Now you change the second bit to 1. Now this is 2 to the power 6. So voltage value is 2 to the power 6 into 0.047, which is 3.011. Now this is less than 4.75. Since it is less, you keep this bit. You will keep this bit. So in the next cycle, what you will do, you will not touch this bit now. You will change this bit to 1. In third clock cycle, you will change 1. Then third bit now we change to 1. Now this is actually voltage value will be, this binary corresponds to 96 into 0.047, which is 4.512, which is still less than 4.75. So you keep this bit also. In the next cycle, what you will do, you keep these bits. Now change this bit to 1. Then check if it is less than or greater than. So basically in successive approximation, you make successive approximations. That is, if V is greater than V in, you discard that one. If V is less than V in, you keep the one. So that is what we had done, right? In the starting, when we change this to 1, we found that V is greater than V in. This is V in. This V was greater than V in, so we discarded it. We changed it back to 0, and we proceeded with the next bit. Then we found that when this bit was 1, V is less than V in. So we keep that one. We then keep this bit, then we proceed to the next bit. Again, this one, we found v is less than vn, so we keep this one also, and we then proceed with the next bit. Check for it. Okay, so the question says what is the output after third clock pulse? So after third clock pulse, your output is this: 0 1 1 0 0 0 0 0. So which is option B. Is this operation clear to everyone? So let us say if we proceeded with in the fourth cycle, we will complete this one. It will be 112 into 0.047. It will come out to be 5.264, and which is greater than V in. So we will discard, and in the next cycle what we will do, we will 011, we discard this one, and then check on the next bit, right? So I hope this is clear. This is the the main functioning of the SAR type ADC, and if you remember this, you can solve any question. Okay, so if there is no doubt, the next question is also very similar. So please try to solve it. Take a few minutes and attempt this question. So now in this case, you have 7 bits, n equals to 7. Your V in is 8.95 volts. Vref is 10 volts. And what you have to find is your resolution will be 10 upon 2 to the power 7 minus 1, which is, let me tell you the resolution, 0.0787 volts. You have to tell the output of the ADC at the start of fifth clock pulse, or clock 0. You start with 0 0 0 0 0 0 2 3 4 5 6 7. You start with this. Clock 1, you convert this to 1. Then check if V is greater than V in or V is less than V in, and proceed till clock 4, and whatever is at the end of clock 4, it is actually start of clock 5. So attempt this. Okay, has anyone got their answer? Okay, C is correct. Yeah, so let us solve this. So you start with 0, 0, 0, 0, 0, 0, 0. Now in first block, change this to 1. Now check, this is actually 64 this 10 into resolution, which is 5.03, and this is less than V in. V in is 8.95. So you keep the bit. Then you move to second block. You have 1. Now you change the second bit since you are keeping this one. And this is 96 into 0.0787. It comes out to be 7.559, which is less than again 8.95. So you again keep the 1. So you keep this one also. So in third block, you keep these both ones. Then now check with the next bit. This is 112 into resolution. That gives out to be 8.818. Still less than 8.95. You can keep the 1. So you keep this one also. The fourth block. Then check the next bit. And this is 120 base 10 and into resolution, which is 9.44. Now this is now greater than 8.95. So you discard. So you discard. So in the start of fifth block, you will have it 1, 1, 1. You discarded this one to 0 and check the next bit 1, 0, 0. So at the start of fifth clock cycle, you will have this. Which is your answer. I hope this is clear to everyone. If not, please let me know. Okay, so a bit lengthy, but very simple question nevertheless. So if there are no doubts, let us move on to the next question. In R2R ladder DAC, if input is 1011, VREF is 20 volts, then found the output voltage. So very simple question. So simply here V out is resolution into V in, and the resolution is Vref upon 2 to the power n. This is a R2R ladder into V in. So everything is given. Vref is 20. You have 4 bits, so 2 to the power n is 2 to the power 4, which is 16, and V in is 1011. So you need to first convert 1011 into decimal form, which will be 11 base 10. So this comes out to be 55, this is 4, 55 by 4, 13.75 volts. IL has given the right answer. Okay, so next question. Again, simple question. You have 4-bit R2R DAC. Output voltage is -5. Input is this. What is the reference voltage? So again, use the same formula. V out equals to Vref upon 2 to the power n into V in. 1001 V in is 9 volts and V out is -5. So you have to find Vref. Yeah, so 8.89 is the correct answer. So -5 equals to Vref upon 2 to the power 4 into 9. So Vref -5. Let us rename this minus 5 into 16 upon 9, which is 0.89 volts. Okay, so next question. If the resolution of the digital to analog converter is approximately 0.4% of its full scale range, then it is how many bits of converter? So if you remember resolution, first to its full scale range upon 2 to the power n or 2 to the power n minus 1, both would work. So it is given this is 0.4% of, or you can write 0.4 by 100 into FSR. What do you have to find? You have to find N. So you just equate this. FSR upon 2 to the power n minus 1 equals to by 100 FSR. Cancel. 2 to the power n equals to 100 upon 0.4 plus 1, just 250 plus 1, 251. So 2 to the power n should be greater than 251, obviously. So n could be 8, right? 2 to the power 8 equals to 256. So the closest is 8. So it is 8-bit converter. Okay, so next we have again this R2R ladder. What is the output of the following circuit if input B4 is 1, B3 is 1, B2 is 1, B1 is 1, Vref is 8. So all these are 1, 1, 1, 1. This Vref is 8 volts. And your Vout is here, Vout. So for op-amp circuits, this is an inverting op-amp configuration, negative feedback. So Vout is always minus Rf by R, let's call it Rx into Vin. So this formula is true for, let's say, this kind of op-amp, minus plus. So for this op-amp, this is Vout, right? So if you solve this, you can come up to, using this, you can come up to some simpler formulation, but for sake of this class, I will write the final expression that you get. Vout is, so this formulas, what I'm writing here is only true for R2R ladder network. So whenever you see R2R ladder you with op-amp connection, you can use this. So Vout is, yeah, minus 7.5 is the correct answer. Okay. Minus Rf by R into Vref into B1 by 2 plus B2 by 4 plus B3 by 8, B4 by 16. you can use this formula. So be mindful about these B1, B2, B3, B4. So B1 by 2 I have done. You can see like it is 1 by I by 2 current is going. In B2, I by 4 current is going. In B4, I by 16 current is going. So with this, you can map these. Okay, so we will use this formula. So here RF is R, and this whole circuit R will also come out to be effectively R itself. So, so how it comes out to be R effective, you can solve this as 2R and 2R in parallel is R, then this R and R parallel is again 2R, then 2R and 2R parallel is R, this R and R parallel is R and R series is 2R, again 2R and 2R parallel is R, R and R series is 2R, then this again 2R and 2R parallel is R. That's why we have the whole resistance corresponding to this is R for this R2R ladder network. So we have used this R here. So if we solve it, we have minus R by R is cancelling. Vref is 8 into your B1, B2, B3, B4 all are 1. And if you solve it, it comes out to be minus 8 into 15 by 16, which is minus 7.5 volts. So I hope this is clear. Okay, so a very similar question. The next one, just VREF is different and these bits are different. So if you guys can give me the answer quickly, just use the formula V out equals to minus RF by R, or simply in this case R by R, VREF to B1 by 2 plus B2 by 4 plus B3 by 8 plus B4 by 16. So yeah, C is correct answer. So if you solve it, you have 15, 0, this is 1, 1, 1, 0. And it comes out to be 15 into 7 by 8, which is minus 13.125. The option C. Okay, so I hope now you will be able to solve these R2R ladder based questions. Uh, okay, so next question. Again, a simple question. You have what is the resolution of 8-bit R2R DAC? Reference voltage is 5 volts. So simply, can anyone tell me the answer? Option D is correct. Right. So, so I'm going a bit quickly because I want to cover maximum number of questions. These ones are pretty simple. Okay. So again, next question. In the following circuit, what is the output V out here when input ABCD is 1010? Assume logic 1 has voltage at 2.5 volts and logic 0 has voltage of 0 volts. Simply what they mean is Vref equals to 2.5 volts. Okay, so you have this ABCD as 1010. So your V out will be, let's say this current is I. So V out will be minus I RF, right? So this will be virtual ground. So your if we apply KVL here, your Vref is, sorry, V out is minus I times RF, and I will be, this I is coming from here, these four branches. So, and this is ground here, this is 1 volt, this is, assume it to be, sorry, this is, so 2.5, this is 0, this is 2.5. So 1 corresponds to 2.5, right? So it is, you can write it as Vref. So let me write it like this only, 1010 Vref into A by R4 plus B by R3 plus C by R2 plus D by R1. So this current is 2.5 into 1 by 1 kilo ohm plus 0 plus 4, 1 by 4 kilo ohm plus 0. So you have I equals to 2.5 into 5k upon 5 upon 4k. Solve this, it comes out to be 3.125 milliamperes, and your V out is minus I times RF. So it is minus 3.125 into RF is 1 kilo ohm. If you solve this, it is simply minus 3.125 volts. Okay. PIL has got 6.25. PIL, did I make any mistake, or is it something you did wrong? Okay. Dr. Nazia says, when will we have sessions on week 9 memory? Dr. Nazia, we will have it in the on the next Tuesday.
Okay, sir. Thank you.
Okay, so I hope this question is clear to all. So next one. How many comparators are required for 3-bit flash type ADC? So this we have seen many times. Flash type ADC, number of comparators is 2 to power n minus 1, which is 3 minus 1, which is 8 minus 1 is 7. Yeah. So next we have a different question now. In a single ramp type ADC, given R is 2 kilo ohm, C is 0.5 nanofarad, Vi, the input voltage is 3.5 millivolt for the RAM generator. Consider the clock's frequency to be 1 megahertz. If ADC generates the digital output after 512 clocks, find the RAM voltage. So I will not get into details of how the RAM ADC works, but what you should know for this question is the RAM voltage VR is slope into number of clock cycles into time period of clock. Okay, and where slope is given as Vi by RC. So this RC and this is Vi. 3.5 millivolt by R is 2 kilo ohm and C is 0.5 nanofarad. So this is millivolts into 10 to the power minus 3. Keep everything in SI units. Solve this, you get 3.5 into 10 to the power 3 volt per second. Now VR is 3.5 into 10 to the power 3. Number of clock cycles are 512 and time period is given by T equals to 1 by F, which is 1 by 1 megahertz equals to 10 to the power minus 6 seconds. So into time period is 10 to the power minus 6. So this is in volt per second, this is in second, this is unitless, so answer will be in volts. So it comes out to be 1.792 volts. So after 512 cycles, your RAM voltage would reach to be 1.792 volts. So basically RAM voltage is just something which is increasing, some voltage which is increasing with time, you can say. And the slope of this is given by Vi by RC. And you have to find it after some particular 512 clock cycles. What is this VR? This was the question in simple terms. So your answer is trendy. Is this okay? So just remember this. This is like purely logical. If you think slope into number of clock cycles into time period is VR, and the slope is just, you have to remember this. What is the slope? Okay. So last question for the ADC. After that, we will start on the state machines. So the last question is for the flash type ADC. So the question says, so I think it is not very clearly visible. So I'll rewrite whenever possible. So you have a 3-bit flash ADC. What is the decoded binary output? D2, D1, 0. So this is D2, this is D1, D0, MSB to LSB. When this V is 8 volts and this Vin is 4.125 volts. So if you look carefully, if you apply 8 volts here, and this is simply, you have a resistor network, right? You have 1, 2, 3, 4, 5, 6, 7, 8. 8 volts divided by 8 resistors, 8 equal resistors, right? All are R. So simply this 8 volts will divide equally at all these nodes, right? So if here it is 8 volt, here it will be 7 volts, here it will be 6 volts, 5 volts, 4 volts, 3 volts, 2 volts, 1 volt, and here it is grounded, 0. Okay, so now all now what will be our output at each of this comparator? These are all comparators. So at every comparator, we will compare 4.125 with the value at this terminal. So 4.125 is smaller than 7. So this will be 0. This will also be 0. This will also be 0. Now this will be 1. This will be 1. This will be 1. This will be 1. All right. And this last bit we take as it's at 0. So your input to priority encoder is 0, 0, 0, 1, 1, 1, 1, 0. You have to convert it to decode it. Now, the thing with priority encoder is how it works. So in a priority code encoder, let's say you have this 8-bit sequence, then it corresponds to, let's say D2, D1, 0. It corresponds to 0, 0, 0, right? So this is 7, 6, 5, 4, 3, 2, 1, 0. Right? These are just bit numbers. So, or I should write it something like this. Okay. So let's say your if input is 0, 0, 0, 0, 1, 0, then your output will be corresponding to 3. So corresponding to 3, your in binary form is 0, 1, 1. Now let's say your output is 1, 1, 1, 0, something like this. Then also your output will be 0, 1, 1 corresponding to this 3. Why is that? Because it is a priority encoder. It will give priority to the let's say you can say the uh, leftmost one or towards more towards MSB. Let's say it was 1 here and whatever it was here, it won't matter. Your output will be 7. So corresponding to 7, it would have been 1, 1, 1. Or simply you can write maybe like 0, 0, 0, 0, 1, cross, cross, cross. It does not matter what is here in these digits. It will always be corresponding to 3. In your case, we have 0, 0, 0, 1, 1, 1, 1, 0. So leftmost one is this one, which corresponds to 4. It does not matter whatever it is here. Your output will be corresponding to 4, which is 1, 0, 0. It's 4. So your output will be option B, 1, 0, 0. Yeah. Payal has got the right answer. Uh, Dina Shah has given the wrong answer. B is not correct. Yeah, B is correct. Yeah, B is 100. Sorry, I read it something else. Okay, so you both have the right answer. So flash ADC is very simple. You just compare the input voltage with the voltage at every node. And if this is higher, it is 0. If this is higher, it is 1. Okay, so is it clear to all? All right. So let us move on to the next question. Which of the following statements are true about the following state transition diagram of a sequence detector? Assume A represents the initial state. So here you have some state diagram with 4 states, A, B, C, and D. And whenever this is written something is /0 or /0, it means this is the output written. After this slash is always output. And over these arrows is your inputs, what inputs you have given. Okay, so you have to tell what is true, what is false. So first statement is the state diagram corresponds to a Mealy model. So you know we have two types of machine, Moore machine and Mealy machine. So in Moore machine, it is a function of state. Output is a function of state only. Mealy machine, output is a function of input as well as state. Right. So in this one, we see output is only corresponding to every state. So at whenever at state A, output is always 0. Whenever at state B, output is also 0, always 0. Whenever at state D, output is always 1. And whenever at state C, output is also 0, always 0, no matter what the input is. So output is a function of state only here. So this is a Moore machine. So first is incorrect. This is a Moore machine. So how would a Mealy machine would look like? In Mealy machine, you generally have, so in Moore machine, you always write it like, let's say if these are 3 states, some transitions are there. You write, let's say A by 0, B by 0, something like this. This is Moore. In Mealy, it will be something like we have these states A, B, C. Your output we write over the arrows. With input, output is changing. So we write the output over the arrows. Then it generally is because now output is changing with input. This is how we represent Mealy machines generally. We'll come to this later. Okay. So first option is incorrect. This is a Moore machine. Second, minimum 4 flip-flops are required to implement the sequence detector. So this is also incorrect. We do not need 4 flip-flops because how many states we have? We have 4 states only, which is A, B, C, and D. And we can represent it only using 2 bits, 0, 0, 0, 1, 1, 0, 1, 1. We essentially need only 2 flip-flops. So 4 states can be represented by 2 flip-flops. We need only 2 flip-flops. Third one, the logic seek detects 110. So the logic detects one sequence 110. So we have to check. So to verify this, we have to check where the output becomes 1. So you start with state A, your output is 0. Then you go to state B, your output is 0. Then you go to state C, your output is 0. Then you go to state D, your output is 1. So what is the input condition from going from A to D that you get output as 1? So when input is 1, then you go to B. Then input is 0, you go to C. Then input is 0, then you go to D. So essentially you are detecting this path, and your sequence you are detecting this path is 1 0 0. So this is also false. You're detecting 1 0 0, and which is the second fourth option, which is correct. You detect 1 0 0. And the last one is the states B and C correspond to detecting the bit pattern 1 and 1 0 in the input sequence respectively. This is true. As you can see, whenever we get a 1, see from everywhere, when we get a 1 as input, we go to B, right? In all the cases, whenever and we get 1 as input, we go to state B. So B detects 1, and whenever after this one, when we get 0, we get to C. So C detects 1 0, or any of these paths where we get 1 0. So C detects 1 0. So this is also correct. So our answer is option D. Only 4 and 5 are correct. Harsha had written E. Second is not correct, Harsha. Is it clear? Okay. So we have another similar question. Please attempt this. Again, multiple are correct and multiple are incorrect. So you can answer this. Just give it some thought. Okay. So this is again a Moore model. This is correct. Output is a function of states. Then, so this 5 written, you check this output is given inside states, then it is always a Moore model. Second one, minimum 5 flip-flops are needed to implement a sequence director, which is incorrect. You have 5 states. So any unit 2 to the power n should be greater than 5. This n you need, so 2 will give you 4. You need 3 flip-flops, right? 2 to the power 3, 8 is 10, 5, yeah. So you need 3 flip-flops. You can represent 5 states by 3 flip-flops. So this is incorrect. The logic detects the sequence 1 1 0 0. So your 1 is at E. What you detect to reach, if you start with a 1 1 0 0. Yeah, so this is correct. Detect 1 1 0 and 0. 1 0 0 is incorrect. B and C correspond to detecting pattern 1 and 1 0. So you see B detects 1. Always when you have 1, you go to B. But C detects 1 1, not 1 0. So this is incorrect. So only 1 and 3rd are correct. Both Harsha and Payal have right answer. It is option C. Okay, next question. The following state diagram is a dash model and it corresponds to a dash sequence detector. Yes, B is the correct answer. This is again a Moore model. And the sequence it detects is you have output 1 here. So you detect 1, 1, 1, 0, 1, 1, 1, 1, 0, 1. Option B is correct. So next question is this. Consider the following state transition diagram given below. If only D flip-flops are used for realization of the digital circuit, then which of the following are true? Where X is input, Y is output, B and A are the states of flip-flops, DB and DA. Okay, so first of all, which machine is this? Now you see output is written X over Y. If we talk about this is input, this is output. This is a Mealy machine. What was the spelling? I forgot. Mealy machine, right? Output is a function of input now, right? So, so we have to basically realize this state diagram with some flip-flop circuit. So to do that, first what we will do, it corresponds of two steps. First is make state table. Step two is make excitation table for machine. Third is write truth table for flip-flop. Okay. So let us first start with the state table. We will understand this in a minute. So say we have present state, next state, you have inputs, let's say 0 or 1, and you have outputs, call it Y. when input is either 0 or 1. Okay, so here again your x is input, y is output. So you can say we have four states, right? A, B, C, and D. Say A, B, C, and D are four states. And we can also represent these states as in terms of binary numbers like 0, 0, 0, 1, 1, 0, 1, 1. Let me just give this coding here. So this is what is your in given question. B and A are the states of flip-flops. So we will use this B and A. Okay. So anyways, so let us look at the state diagram now. When input is 0 and you start at A, so you are at A, your input is 0. Then you go back to A, next state is still A, and your output is 0. So it is A and 0. When input is 1, you start with A, your input is 1, you go to B, and your output is still 0. So B and 0. Then you start with B, your present state is B. Then if your input is 0, you go back to A, and your output is 0. So it's A, and your output is 0. You are at B, your input is 1. If input is 1, you go to C. So here we will have C, and your output is still 0. Now present state is C, input is 0. If input is 0, you go to D, output is still 0. Okay, D, output is still 0. If you get 1, input is 1, the next state is also C, output is still 0. Then you start with D, your input is 0, you go to A, and your output is 1. Right? If input is 0, you go to A, and your output is 1. If input is 1, you go to B, and your output is 0. So it will be B and 0 here. So this is your state table, right? So in excitation table is not much different. So let's say you have some columns here, input, bn, an, bn plus 1, an plus 1, output y, and what would the flip-flops represent? db and da. Okay, so let's start one by one. Again, these b and an are nothing, just these states a, b, c, d. So if I write b and an also, 0, 0, 0, 0, 0, 0, b is 0, 1, 0, 1, c is 1, 0, d is 1, 1, right? So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay, so this is nothing but A, B, C, D, A, B, C, D, right? If input is 0, you are at state A, the next state will be You are at state A, input is 0, you get to state A again, and output is 0. Same thing you write here, still remain at state A, which is 0, 0, and output is 0. Input is 0, you were at state B, you go to state A again, and output is 0. Same here, 0, 0, output is 0. Input is 0, you were at state C, you go to state D, output is 0, state D is 1, 1, and output is 0. You were at state D, input is at 0, you go to state A, output is 1. Go to state A is 0, 0, and output is 1. Now when inputs are 1, input is 1, you were at state A, you go to B, output is 0, sorry, 0 here. State B is 0, 1, output is 0. You were at B, input is 1, you go to C, output is 0. C is 1, 0, output is 0. You were at state C, input is 1, you stay at C, output is 0. You are at state D, input is 1, you go to state B, output is 0. B is 0, 1, output is 0. Okay. So we have filled all these columns. Now we just need to connect the flip-flops. So for flip-flops, D flip-flops, you know Qn plus 1 equals to D. So simply Bn plus 1 equals to Db and An plus 1 equals to Da. And simply write it like here. Same 0, 0, 0, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 1. Okay. Now the next step is you write dB or dA as a function of input. Let me call it x. X comma b n and an. Similarly, dA also as a function of x, bn and an. For this, let us make k-map. X bar and x, you have d bar, a bar, b bar, a, b a, b a bar. Right. So similarly, we will make the same thing for dA also. For dB, you have 1 when it is 0, 1, 0, 1, 0, 1, and 1, 1, 0. So 0, 1, 0, this is 1. You have 1, 0, 1. This is 1, 0, 1. So this is 1. And 1, 1, 0. It's 1, 1, 0. This is 1. And for DA, DA is 1 at here. 0, 1, 0. This is 0. This is 1, 0. So here it is 1. Then at 1 0 0, this is 1 0 0, and it is at, this one is at 1 1 1 1 1 1 here. Okay. So now we can make groups. This is one group here. So it is simply A bar B plus, this is what, X A B bar. And your DA is, so I think there are no groups can be formed. It is simply X bar A bar B plus X bar AB plus X bar A bar B bar. And you also need to tell Y. So for Y also we can make a table. So Y is one only in one condition, 0 1 1, just X bar BA. Y equals to X bar BA. So this is your required answer. Option D is correct. I hope this is clear. So it is very similar to when we do flip-flop conversion. We first just made, so what we are, our objective is to convert the state table with some flip-flop circuit. So we first made the state table with the help of this state diagram. Then with this table, we made this excitation table. Yeah, these are just 0 0 means A, 0 1 means B, 1 0 is C, and 1 1 is D. And this is just present state. This is the next state. This is the output. And this Bn plus 1 corresponds to Db. This is just flip-flop output. An plus 1 is flip-flop output for D flip-flop in DA. Then we wrote DA, BA, Y, DB and Y in terms of input X and A and B, which was asked in the question. Is this clear to everyone? It was a lengthy question, but nevertheless very easy. So I solved it quickly, so I will upload these notes as soon as this class ends, so you can maybe go through it once more. So if there's no doubt, I have one more question for today. Easy question now. We again have a Mealy machine. So we have this input sequence X given as this 1 0 0 1 1 0. We have to tell the corresponding outputs of Z. What is the output? We have to tell, which is simply they call Z. Okay, so can anyone attempt it quickly in a minute? So you start with S0, then give these inputs, then check what is the corresponding output. Yeah, option D is correct. So let's see. Start with S0. So when your input, your inputs are 1, 0, 0, 1, 1, 0, 0. So when your input, you started with S0 when 1 came. So 1 input is here. You go to S1, your output is 0. So you go to S1 and your output is 0. Then from S1, 0 came. So you go to S2 and your output is 0. Then at S2 again 0 input is there. So with 0 input you go to here itself and your output is still 0. Still at S2 output is 0. Then you get 1 again. Then you get 1. This is the 1 path. You go to S4 and your output is 0. Then from S4 your input is again 1. So this is the 1 input line. You go to S3, your output is 1. Output is 1. Then you get 0. So 0 means you go to from S3 to S5, 0 by 0. You go to S5, your output is to S5, your output is 0. S5 you again get 0. Then you go back to S2, your output is 0. This is actually what is asked, Z. So Z is 0, 0, 0, 0, 1, 0, 0, which is option D. Okay, so these are all the questions that I had for today. If there are any doubts, you may ask, else we will end the session. Okay, thank you everyone. See you next Tuesday.